You have to be in front of your camera.
Yes, please.
So it's a great honor to welcome Thorsten Zander here. I remember Thorsten when he came 20 years ago in our lab with 6 or 7 students. Some of them stayed at UCSD. And at the time, he was assistant professor at Berlin University. Now he's a full professor at Cottbus University, and also the founder of Zander's Lab, which is a company employing more than 40 people and that has gotten the largest BCI grant ever, $30 million in Europe. So yeah, we're very grateful to have Zander here. And if he has an EEG, you know, he can read your mind.
Be careful. Thanks, Arno. Thanks, Arno, for the kind introduction. Yes, I'm very happy to be back in San Diego. It has been a while, and I'm happy to show you the latest results we have in Zander Labs and the NAFAS project. So I'm going to speak about neuroadaptive AI. So neuroadaptivity is the idea that we use passive BCIs to adapt a technical system to the human mind. And specifically in neuroadaptive AI, of course, we look at large language models and physical AI. And the idea is there that we tune these systems to the mental state of the person the systems interact with. Okay, so yes. No. Oh, sorry. So let's take a few steps back and look at tools. I mean, technological systems we use today are tools, but we started from something else. When you look at this screen, you see very basic tools, which look a little bit silly to us, but they enabled mankind to do the things we do now, to build stuff. And while using these tools, we created technology. And when we speak about technology, we think about something like that, more like a robot, which is more humanoid, which is capable of doing things on its own, has some autonomy. But it's just a picture, right? We don't have that yet, really. I mean, we're starting to build that now, so they're coming to the market. But this is what we idolize. This is what we want to see. And of course, we see self-driving cars, and that's fascinating. And it's crazy to see that. I mean, when I sit in my Tesla, I can't believe that it's doing all that stuff. But still, it's not perfect. It's still far away from being as good as a human, I think, in many regards. And even more, when we look at large language models, we see it can do crazy stuff. It can communicate like we do, maybe, but it can create language which looks really important to us and meaningful to us. How much that is dependent on our mind, that we read something into that, or how much is really intelligently behind that is at the moment a bit unclear. So what we are asking is basically, when we look at the human computer or human AI convergence, how far are we? Can we create adaptive systems? Can we create autonomous systems that can reach out to us and be on the same level, on the same eyesight as we are? So the question is, how can we solve that? And there, the big problem is, one of the big problems is alignment. So machines that understand how we see and interpret the world, how we feel about the world. And that is a crucial step we haven't taken yet. And my suggestion to solve this problem, to solve the alignment problem, to make machines empathically understanding us, is a passive brain-computer interface. So BCIs allow to assess information from the mind, from the brain, in real time and correlate it to the context. And most of the BCI research is focused on direct control. So like mental butt presses, it's like a real butt press, but you just do it with your mind. But more than 20 years ago, I suggested to use it also for implicit interaction together with Thorsten Kothe, who's still here in San Diego. He's one of the guys who joined me at the time to the sports center and stayed here. So the idea is that you can read information out of the mind that is related to the context the mind is perceiving. And with that, we understand how the mind is interpreting the world. You can use the same technology, the same algorithms you use for classic BCIs, but the difference is that you don't need to focus on that. You can interact with the world freely, and your mind is producing all the data anyhow, and we can read it with the BCI and understand how you interpret the world. One example is, which shows what you can do with that. It's not really useful, to be honest, but it's a good example to showcase what you can do. It's something we call mind tris. It's a Tetris game which you play with standard input. So you don't control the tetraminos with your mind. You do that with your hands. But the speed of the tetraminos, how quickly they fall down, is related to your mind state. So the idea there is basically the more stressed you are, the quicker they fall, which is a little bit mean. So the idea there is that you need to stay calm in a stressful situation. And the better you can do that, the better you can play this game. So she's playing that, and she's a little bit stressed now. The speed of the music is indicating the stress level. So it's going rather quick. But now she tries to relax, and the music is slowing down. And with that, also the speed of the tetraminos falling down is going slower and slower and slower. So there's a passive BCI reading out her workload, and the less she's stressed, the slower the tetraminos fall. And when she can stay for 20 seconds in a really relaxed state, she gets an extra bonus. The lower line will be deleted, like you see now. So she's now doing two things at the same time, playing Tetris and trying to stay calm. So that is an additional channel for this game. You're still your main interaction. And you have the mind state as a secondary information channel. Okay, that is an example how we can connect to technology in a different way. So we're really used to translate any thought we have into direct commands to the machine. And this is how we know it works. And it's really confusing for people that you can do something differently, that you can do some implicit information and send it to the machine. But next to adapting a computer game, we can go into the alignment sphere. And I will misuse now the concept of qualia from philosophy to explain what I mean with that. So when I talk about the color, certain color shade of red, I have very specific associations to that. I have a feeling when I see this color of red, the shade of red. It means something to me, but I can't really explain what it means to me, to you. I could give you some fragments of my experience, but this is what the qualia problem describes. You never can experience it in the same way I do. And I think that's related to my experience of my life. I mean, maybe I saw my mother in a dress in the same color of red, a shade of red, or I had a toy or whatever. All the experience I had in my life accumulates in this experience when I see that shade of red again. So, but if I can't explain that to you, how can I explain that to a machine? And if I want a machine to understand me, maybe not in the shade of red, but in any way how I understand the world, how do I communicate that? I mean, I can try to verbalize that, but that would be a lot of effort to do. So this describes the alignment challenge. And next to this communication problem, it's also the case that AIs live in a different world. I mean, an AI, an LLM is trained on words. It only knows words. That's it. We understand the world. We associate these words to real things. And to bring these words together is really difficult. So how do I describe to an LLM what playing soccer really is? I mean, it can describe it, but it never experienced that. And I would like to utilize a story told by Stuart Russell about a kitchen robot. I changed it a little bit to my own liking because I like cats, and so I changed the main actor in this, or the second main actor in this story, to a dog. So let's assume we have robots in our kitchen. So in 20, 30 years, everybody has their own robot at home, and that robot is perfectly cooking the meals for us. It knows what is good for us, it knows what we like, and it's healthy what it cooks, and also ethically aligned with our own understanding. So we only eat meat on Wednesdays, and the rest of the week we don't eat meat. And on a Wednesday morning, it comes to the kitchen and wants to cook something for us. It's really happy to cook the best meal we like. And then Robert goes to the fridge and sees, oh, there's no animal protein in the fridge. That's a problem. But we have an adaptive system, an autonomous system, so it can solve problems by itself. So it looks around, takes a knife, and tries to find animal protein. And at that moment, our dog comes around the corner. Okay, I stop here now, right? But you get the idea. So the question here is, how should the robot know that it's good for us to kill chicken or pigs or cows, not even kill them, but really treat them really badly, but not the dog? I mean, it's even for me hard to understand why we make this discrimination. So, and it's really difficult for the robot to understand where our values are. And when you maybe in a different part of the world, then it's good to eat dogs or cats, and maybe not good to eat pigs or something like that. So, of course, you can now say, we can easily explain that, right? Don't cook my dog, right? And that's fine. But then, I mean, extrapolate. How many things you need to explain? I mean, you get a robot and then you sit there for the next 2 weeks continuously explaining what it should do or not do. So that's the problem, the alignment problem. And my suggestion is that we can solve this problem by using passive PCIs. So to be very clear here, a lot of people are working or were working on the alignment problem. OpenAI had the super alignment team, and they had 32 coworkers there that extensively worked on that, and then it was dissolved because they didn't make any progress, to be honest. There is no super alignment team anymore, and they now claim, yeah, it's all done, it will learn it by itself, but it's not the case. So we have actually no real concept to create something like empathy in a machine. So, and let's take a step back and understand how we learn. So we come to this planet with a very young, small body and a great brain, which doesn't have much experience. And then we start to explore the world. I mean, think about a baby lying on its back and moving its arms, right? This is how we explore the world. But then we have parents who tell us good things. So my mother might tell me, don't touch the hot stove, and then I do it, and I feel the pain. I see, oh, it's good to listen to my mom. But also I look out of the window and I see a leaf falling down, and it was there, and then it fell down, and then I might get the concept of gravity. So I have a lot of context-sensitive training data, which is perceived through all of my senses, which are great sensors to identify the world. But still, it takes us, in Germany, 18 years, I think here 16 years, until we're allowed to drive a car. So we have the system, if I may refer to a person as a system, with powerful brain, great sensors, a lot of annotations, and we still say, okay, wait some time until you can act in the world freely. Comparison to that, we might have an AI that we dump data into. We take basically the full internet and dump it in there. Then we press a button and say, learn from that. We don't annotate anything. Language by itself is somehow annotated. It has intrinsic meaning, but it needs to translate that into its own language and learn from that. And to be honest, for a very long time, even before LLMs, I asked myself, why do we do that? I mean, it's obvious that this is not perfect. I mean, we see that we have self-driving cars and we have large language models, but that's not the optimal way to train them something. And why I was so concerned is, or irritated, is we have everything available. We have the human brain. The brain has learned to understand the world. So why don't we use that as a tutor, as a teacher for machines? So the idea is basically this brain is interpreting the world, and we have sensors that can identify how this works in the brain. So we can translate that with our cool machine learning and AI algorithms into something and connect that to an AI. And if that AI sees, or the machine sees the same context as I do, it firstly perceives the world and learns to understand, to interpret the world from my brain signals. So with that, we don't need to replicate each single process in the brain, but the brain is processing everything, and then the output of that, this one bit which comes out of that, is given to the machine, which can process the world by itself. It has cameras, it has processors and whatever, but the meaning is missing. And this one bit we have there from the BCI can provide that meaningful information. So that was very abstract. And now look at it in this scenario. It's just an idea, right? So let's assume this guy over there is the expert in putting a screw into that machine. So he's the best guy. Nobody can do that better than he can. And the robot wants to learn that. So when we talk to this guy, he likely can't explain why he is so good. He says it's like in the textbook. I do exactly what is written in the textbook. But when he tries to explain it to you, here again we have the qualia thing maybe, he can't transfer all his skill to you. So how can he transfer that to the machine, to the robot? He's observing the robot, and he's drilling the screw into this machine. And while he's doing that, his brain is analyzing everything and is constantly feeding back information to the robot. Every minute change will be interpreted by the brain, and this information is fed back to the robot. And this is how the robot can learn from the best person to do the task in this scenario. That's the vision I want to describe. So, and like mentioned by Arne already, I've been talking about roughly this idea, not exactly that, for 25 years. And in the beginning, I was in San Diego. I will never forget that. I was in a car with some older professors, and I was telling about my ideas. And they were not unfriendly. They meant it well, but they laughed and said, come on, grow up. The world doesn't work like that. So it was really hard work to explain that to the world, that this idea is powerful. And as lucky as I am, the German government got aware of it 3 years ago, and then they decided to not distribute their money on multiple projects, but to combine it and put it into one project. So they didn't directly give it to me. I had to apply for that, and many others applied for that too. But then we won, and we got the 30 million euros in our pocket now for 4 years to bring this idea to the world. So for 20 years, I did scientific research, and now we want to transition from the laboratory to the real world. And therefore, this money is intended. It's not enough to build products. I mean, if you leave the scientific world and go into the industry, build something, 30 million is not that much. I mean, for scientific research, it's awesome, but it's intended to do this step, to do the transitioning, and then hopefully get investors to do the next steps. So we have 30 million euros. That's an old number. Now we have 54, not 45 people working with us, and we have 10 partners in Europe. And the first thing is we need to get data from the brain. And here you see, most of you will know that you have different options, different mechanisms to read information from the brain. You can go into the skull, into the brain, and get very precise data. And here in the US, it's the most common thing. Look at Neuralink and other companies that they work on implanting these sensors into the brain. I personally have a problem with that because I really don't see that people who want to use ChatGPT will firstly have a hole drilled in their skull and put something into the brain. But I mean, the investors who invested 250 million into Neuralink are convinced that this is a good idea. But the next thing is more scientifically, you get a better quality with these sensors you can put into the brain because they're really close to the source of the signal. But with that, it can really only read information from that spot. If you want to have a complete information of the mental state, you need to put a lot of sensors in there because you will only read locally. So I think you need something like 40, 45 electrodes in the brain to get the full state of the mind. Maybe there are other sensors coming out in future, but what they're working on now, currently, would need a lot of holes being drilled in your skull to get all the data. So we're working with EEG because we can put it on this scalp and get a lot of information. Yes, it's more noisy, but it's distributed. You can get a broader picture of the brain. But here you see some amplifiers and some electrodes. This is how usually the EEG setup looks like. On the left-hand side, you see that from 1984 or something, and then from 2010 on the right-hand side. It looks a little bit more nicer. It's a little bit more marketing, but basically the same system. Nothing much changed there. And on the bottom, you see the large amplifier, which are, boxes on your desk or something portable, which is good. But also, at the same time, if you go to BCIs, each single detector, each BCI that detects a certain mental state needs to be calibrated. So you need to provide exemplary data and then train your algorithm on that. And so before I want to use a surprise classifier or error classifier or something like that, I need to provide 20 minutes of data, and then after that I can use it. And then the next time I want to use it again, I have to do that again. So it's not transferable. And these are two big problems in the BCI world. It's uncomfortable to wear these caps, takes a lot of time, and looks ugly, and you need to calibrate all the classifiers. So in NAFAS, we did approach this problem, the first problem of the wearable systems, with the so-called C-grid idea. It's an electrode grid you glue behind your ear adhesively. It's unobtrusive, it's easy to wear, easy to apply, and you can extend that. So we decided to add more electrodes to the front head. And we wanted to reduce the amplifier that you can put it behind the ear, that you don't have to wear it somewhere else, to also shorten the cables. And the next thing is we wanted to do all the processing locally. Why do we want to do that? So we aim at large-scale use of these systems. And when we talk to people and say, hey, come on, we read your brain state and we interpret that. So we upload it to our cloud and we do something with that. It's not creating trust in people. And I think that is a big first step we need to do. We need to convince people that we not try to manipulate them. We'll not read anything out of their mind, which we shouldn't. So the idea here is basically that all the processing for the classification is done on this chip. And after 10 seconds, the EEG is completely deleted, and only the classifier output, only the mental state information is there. And that is information you understand. Do I want to give out my emotional data, affective data right now? Do I want to give information about my surprise, about my error responses? Everybody can understand what that means, and you can press a button, and we have multiple buttons on there. You can decide what you want to send out or not. So you have control of what you send out, and you understand what it is. So, and that is the Zypher headset you see here. That's the first prototype we have, which is the realization of the idea you see on the left. That is the amplifier. So it's really small and lightweight. And interestingly, the signal quality is, in our testing, better than the ones you can buy commercially. And this is what I should probably not say, but this amplifier is easily sold for less than $1,000. Maybe even way, depends on the amount of system we produce. So, and the other system costs $30,000 or something like that. So that is really a huge step. And that is the first prototype. It can get smaller. It's like a mobile phone size. That's the system on a chip where we do all the processing on. We can run up to 8 classifiers on the system. Yes. But the question is, of course, yeah, it looks nice. You can glue something on your skin, and then you have the amplifiers. So how well does it work? So we went to the ERP core, which is a way to create signals in the brain. It's a collection of paradigms to do that. And this is what we collected. So you see the different mental states on the left-hand side, and then you see different patches on the right-hand side. And when you look at that a little bit closer, you see on the left-hand side the normal EEG, and on the right-hand side, the two versions of that are what we collect with our patches. It's not exactly the same thing, so it's probably not good enough to do neuroscientific research, but for classification, for doing BCI, where we do anyhow a reduction of the data, it's good enough. How good? So here you see the accuracy. The first dot on the left is the accuracy with the full cap, and the dots on the 2 dots right next to that on the right are the accuracies, the classification accuracies we have with our patches. So we only use a few 3-4 percentage points of classification accuracy with the system. But the next problem is the one of calibration. So when we want to collect 20 mental states at the same time, we need to go 20 times 20 minutes, which is 400 minutes, to calibrate the system. And this would mean you have to do 5-6 hours to just calibrate your system. Nobody will do that. So we want to generalize the classifiers. So we collect data from 4,000 subjects. It's basically a big data approach. And we put all the data into the classifier that it can generalize. So we have a plug-and-play application. What does it mean? When we compare the accuracy of a classifier that is trained on, at the moment, 1,400 data sets, but hasn't seen your brain yet, and we compare that accuracy to one classifier that is trained on your data, it's basically the same. Statistically, it's no difference. So we can directly now, at this time, collect 6 classifiers without any calibration. And it's not that long ago I did that. I was sitting in the lab and I said, okay, well, let's collect surprise. And we could start with that. Let's collect workload. Or let's add error potential as well. It was just a button click. So we can really modularly add any classifier to your experiment or to your application, which is really cool. But it needs to also be transferable between contexts. So if you look at the literature, most of the classifiers are task-specific. But let's go for workload. When I have a workload classifier that is identifying math, that's cool. But usually I want to have workload in any kind of situation. So we want to have a classifier that is not discriminating between. Maybe you want to, then you can go to that, but we have classifiers that can be transferable between contexts. And then, like you've seen, our patches, Cypher patches, look different than a normal cap. That's good. But if we, let's say, in 5 years, find a new configuration of electrodes, we don't want to start again. We need to collect 4,000 data sets again. So we also have designed a mechanism that you can transfer from the data we collected to any kind of montage, any kind of electrode setup without any loss. So we have now these classifiers available. And the good thing is, it's more than that. So we try to select these classifiers as dimensions, independent dimensions of mental state. So we did a study with Airbus, and they wanted to see something called automation surprise. Something is happening on the cockpit, and the pilot is surprised from the automation. So it's a mixture of error responses and surprise. And we trained a classifier specifically on automation surprise and compared it to a two-dimensional classifier that was trained on surprise and error responses. And we could recreate the classifier with our base classifiers. So now let's get into some examples. Here we did a scenario where we asked the subject to look at the game cards, playing cards on the top. She should select one of these cards and keep it in her mind. And her task is, our system should not identify which card she selected. She could win money if she would fool the system. So the system is trying to read out of her mind which card she selected. The only constraint was she has to look at the screen. She can't close her eyes. So that was the only rule we gave her. And she was intended to find out how to fool the system. So she writes it down for us for the video. She selected the 7, but the computer doesn't know that. Now the system is probing her mind, something we call cognitive probe. It's showing her briefly each card and looking at the reactions of her mind to that. And it does it multiple times and gets more confident over time. And here, after 3 runs of all the cards, you might have seen the 7 there, and it did something to your mind. Last run now. After 3 runs, the system has to decide what is the card she selected. And it found the 7. I mean, that's not too surprising when you look at the literature out there. But when you see what you can do with that in a realistic scenario, it's cool and a little bit frightening at the same time. So we'll jump to the end of the video. Here you see all the runs we did, and it will indicate how often it worked out. And it was quite successful. So in the end, we got, I think, 80% of the cards we detected with our classifier. So that's one example. Now, from that simple example, let's go to something more complex. Neuroadaptive reinforcement learning or reward learning. So the idea is, let's assume you have an AI. It's basically the scenario we had with the guy who was the expert on building the machine. So I chose ChatGPT's logo here. We have the AI, and that AI has a world model. It's a model about the task. It's the bars on the bottom. And then the actions of this AI can be transferred to a user. So you can observe the output of ChatGPT. And then your mind is responding to that. So you get mental states out of that. You can feed these mental states into the world model, into the model of the system, and adapt that. So these x1 to xn could be level of surprise, degree of error, current workload, and that is annotating the actions of ChatGPT in this example. So we already do that. There's reinforcement learning with human feedback, where people basically read a page of text and say good or bad. This is how ChatGPT actually got successful. I talked to one of the main developers of ChatGPT, and he said, he confirmed my idea that this human feedback was a key element why it got suddenly so good. So when you look at ChatGPT 2.0 or 2.3, one of the main contributors was the human feedback. But here we can do that not at one page, but at every word. Every word can be annotated by the mental state. And it's not only one value like good or bad, it's a continuous value of multiple dimensions of brain states. So some of you might know that. It's a study 8 years, or 9 years already ago, published in PNAS. We had this cursor over there. This is a red dot on the left. And then the target here on the upper right. And the cursor should jump to that target. It can only jump to adjacent nodes. And the observer is providing feedback by looking at the cursor. So this would be interpreted by the mind, and this would be interpreted by the mind. We just asked people to watch the cursor jump, and they would say, okay, yeah, it's close, good. But then they were not happy with this one. So they were observing the cursor jumping around. They did it for a while. We invited 24 subjects, and they were perceiving the cursor jumps, and they just knew, observe the cursor, and we will record your brain data. They didn't know anything else. But from that data, we collected the brain results, the brain responses. And what we did is we identified positive responses and negative responses. So the classifier could identify whether the person would interpret that jump they have just seen as positive or negative. And here you see the length of the arrows of the cursor. And the length indicates the likelihood to go into that direction. In the beginning, the cursor is uninformed. Every direction has the same probability. Then it jumps to the right in this example. And we ask the brain and get a response. And this response is positive. We learned that already. Then we say, okay, in the next jump, go more likely into that direction. Then it, for example, goes to the upper left. And we ask the brain again, get another response. And that is a negative response. And we say, okay, that was bad. And so the cursor learns step by step where to go. And finally, we see after a few jumps, okay, it must be on the right, upper right. There's nothing else, the same thing, just a different perspective on that, than creating a model of directional preferences of that person. I extract the situative model of preferences from that person. So the cursor goes there, we ask the brain, we adapt the model, and the cursor moves better. Same thing, just a different perspective on it. So now you will see a video, which is real data. On the left-hand side, you see the cursor jump that was perceived by the participant. On the right-hand side, you see the model, which was not seen by the participant, of course. So the first jump is bad, we reduce the probabilities. The next jump is good, we increase the probabilities. Step by step, the model is refined. And after a few jumps already, the cursor knows where the target is and goes to the target. We can do the same on a 6x6 grid, which takes a bit longer, but is even more effective here. And we ask people, do you realize something going different here? And they said, yes, it's much faster. And we asked them, do you know why? And they said, yeah, maybe the target is in the upper right corner, the cursor prefers to go there. They had a lot of ideas, but none of them knew that they were influencing the cursor. And here it's still going randomly, or not randomly, but statistically. But after a few jumps, the cursor is already hitting the target. So how can we interpret that? So like I said, it was published in PNAS a couple of years ago. And when we look at the performance of the uninformed cursor, we see it needs, on average, median, 27 jumps on the 4x4 grid and 90 jumps on 6x6 grids to randomly hit the target. With our really simple form of reward learning, we can reduce that to half of the jumps on the 4x4 grid and 1/3 of the jumps. That is also quite close to the perfect jump. So what does perfect jump mean? If you would give perfect reinforcement, if the algorithm that is rewarding the actions would know where the target is and give the best possible reward, it's very close to the 13 already. With this simple brain extracted signal, which is an accuracy of 80% of detection, we almost get to the optimal there. And when we look at 6x6 grid, it's even more powerful. We go to 1/3 of the jumps, and we're also quite close to that. When you look at the circle on the upper left, you see that we can not only look at the direct good or direct bad jumps, but any angle in between. So if we're a little bit off of the cursor, of the target, we can color code that. And then you see that you have a linear correspondence of the brain signal, of the brain response to the angle of deviance. So we can also read more fine-tuned that you like that a bit or didn't like that much. And we could locate that in the medial prefrontal cortex. So I think this is something which is related to predictive coding. And basically, that is part of the reward function of the human brain itself. So predictive coding simply says we have something like reinforcement learning in our brain, and we can tap into that reward function. And here's an example how cursor moved and how the model derived over time. And that's maybe a little bit more identifying how it worked. That is an old study. I mean, some of you might have seen that already. But we recently did, together with the German government, we wanted to predict how the brain would respond to movements. So we fed data from this experiment into an LLM, but only on certain jumps. So it would see if the cursor jumps from 1 to 3, we have a classifier output of 0.8. And we gave some examples of these jumps, and we let the LLM learn from that. We tuned the model to understand how the brain would respond to certain moves of the cursor. And then we trained different models, different LLMs, and asked it to predict what the brain output would be on previously unseen jumps. So it looks at the jump it hasn't seen before, and it should predict how the brain would respond to that, and it has an accuracy of 93%. So the LLM could learn from these examples how your mind would respond to previously unseen tasks or actions. That is a form of alignment. I mean, the system predicts your brain data from some examples. The next thing is we gave it autonomy. You just asked it to move the cursor in a way that it makes you happy. So it should fulfill the task, but also create a positive mind state in your mind. And we had different prompts over there, and the more detailed we got, the different the results were. So you see AG is the agreement of the person. When we gave a very simple explanation, we had an agreement of 64, something like that. But when we explained to the model better how your mind works, it could increase the agreement to 74 on average. So it would act by solving the task in a way that you agree to it. And that's direct definition of alignment. The system tries to fulfill the task, but with your agreement, with your acknowledgement of it. And that was ChatGPT 4.0. So now it would even work better. But that is fulfilling the assumption that we can create some kind of alignment in a machine based on passive PCIs. The next step is categorical learning. So when we look at human learning, one of the best descriptions of our learning is categorical learning. So we have an idea of different categories you have in your mind, and then I have things I can pour water in, and then one subcategory of that is a glass, the other one is a mug, and then we can transfer information we have learned of these things to other things. So when I see a zebra for the first time, but I've seen horses, I can transfer my knowledge on horses to the new idea, the new category of zebras, and that helps me. But when you look at machines, how do we learn there? We do something like classical machine learning. We have two classes and do supervised learning. Or we do some kind of reward function we've seen before, which is nothing else but clicker training. You say yes or no, good or bad, one class or the other class. And that is compared to categorical learning, a real weak description of learning. So why don't we do something like categorical learning on machines? So why don't we do that? Why don't we transfer that? Because we can't explain it. We have no way to extract all the categories of we have in our mind and explain that in a way to a machine that it works better. I mean, we do that partially with LLMs because we have language, and that is basically categorical. But how can we generalize that? That's a big question. And we can again use a passive PCI for that. So this is just a very abstract task, but let's assume you see a number of symbols on the screen, and your task is to answer the question, are there more B's in a circle than Q's in a square? And then you say yes or no. So you get this example, and if you get this task, you will read that, and you can identify how many B's in a circle are there, how many Q's in a square are there, and then you can answer this question, and you can say thumbs up, thumbs down. This is how we do that. So how do you likely do that? You identify firstly the Q's in a square and the B's in a circle, and then you identify these are the good ones, these are the bad ones, and you can answer the question. All the others are not relevant anymore. So you would say, no, it's not true. We don't have more B's in a circle than Q's in a square, and that's it. Okay, and then we can, of course, train a machine to do the same thing. How do we do that? We do supervised learning. We give the examples of the sheets where you have all the symbols on the screen, and then you say, give your response to that. You give the label to that data. And then the system would learn like this. It would, over 1,500 samples, go to an accuracy of 82% or something like that. That is standard machine learning. We did that really on the data, and the accuracy was what you see there. It learns over time, gets better. But then we did the same thing, but added a layer of mental states to that. We extracted 3 passive PCIs from the mind of the person and fed that, only the 3 values, into the machine learner. And you see the red curve is the outcome of that. What is the difference? In the end, it's really at 100%. It doesn't make any mistake anymore. So it really fully understood the question, the task. But it almost everywhere, with some overfitting at 500 samples, is 20% points better, just with these few numbers added to that. And also it kickstarts. I mean, after 150 trials, we're not at 50%, we're at 68% already. It's just one example how this passive PCI can make a difference. People say, come on, it's so noisy data. It's you have an accuracy of 80%. This is not meaningful. When you look at that, you see it is meaningful. So now a little bit more practical examples. So we went to a speech-based large language model, so verbal interaction with the LLM, and we did a experiment. So we did a spelling bee. So the LM did a spelling bee task with you, non-native speakers here. And here you see the easy word example.
You to pronounce the word fruit out.
Fruit.
So that was an example, pronounce fruit, do that, and then spell it. And we collected the workload over that. A more difficult task was then this word.
The word for round 9 is anti-disestablishmentarianism. Take your time and go ahead and pronounce anti-disestablishmentarianism.
Could you say that again?
Okay, so we did some experiments with that, and you see 2 subjects here. And on the x-axis, you see 1 to 10, that's the difficulty of the spelling bee task. And on the y-axis, you see the workload output of the classifier. And on subject 1, you see there's a basically linear increase of workload with the increase of difficulty. And on the second subject, you see that it breaks down after task 7. And that is where the person gave up. They said, I can't do that anymore. And so it's really reflecting the workload in this scenario rather well. It's nothing super surprising, but it's more practical application of something while interacting with an LM. You can identify mental states.
The
next thing is transferring the agreement classifier we've seen from the grid paradigm to another task. And So here you see person that was
Okay, let's continue. The dessert was so good it was hard to resist. How expected felt the word resist from 1 to 5?
5.
so here they had a scenario on the top left, and then there's statement, and that ended in a word that was either very expected or unexpected.
Okay, let's move on to the next sentence. While eating the soup, Ariel could taste the mold. How expected felt the word mold from 1 to 5?
1.
And we see an agreement of the classifier we've trained in the grid paradigm to these words. So this is just a test. Can we transfer these classifiers into real world settings? And now we transferred that to a robotic task where we had a VLA, Vision Language Action Model, that was fed with brain data that was coming from a person observing the task of the robot. So the person is looking at the task of the action of the robot. The robot should move the red cube into the red basket and the yellow cube in the yellow basket. And then the person was watching that person, the robot, was interpreting all the time continuously the actions of the robot. And then this was fed back into the reasoning of the robot. And it could then improve the actions of that robot continuously. So we really inserted a statement, the human dislikes what you just did right now, into the reasoning of the robot. And you can see on the left hand side that the trajectory with mental states had a higher AUC than only the trajectory. So the LM, who should interpret that, could only see the trajectory of the movement or got the trajectory plus brain states. And again, here you see that this robot interaction, by feeding information to the reasoning of the robot, could be improved. The next thing is that we showed videos of car crashes or near crashes. And we could identify from that with our classifier, with the classifier of the grid paradigm where the cursor moved, we could identify whether the person would think that is a crash or not. So these are just some ideas, some examples we're trying to figure out now together with some partners to build something that could really improve the learning of LLMs. I mean, this is not, I mean, I went quickly through that. It's not a final result. It's just some first evidence we have collected there. Oh, that is on German. I'm very sorry for that. It should not be in there. Sorry. But basically, it is a first version of alignment. I mean, you interact with the machine in a same scenario, and through the passive PCI, we can transfer some of your interpretation to the machine. This could be used in autonomously driving cars. So here you see the boy playing with a ball. And when I would sit in the car, I would immediately look at the boy and see whether he saw me or whatever, get an idea, get a gut feeling for that, whether he would run on the street or not. I mean, the Waymo car I used in San Francisco recently was very careful in that situation and didn't have a full understanding. I've been told when I grow old, I will be likely taken care of if needed by a robot, not by a human. And I truly believe the robot will not do anything bad. I mean, it would treat me, support me well. But I can be sometimes grumpy or very stubborn, and a human person would understand that today I'm really grumpy and I want to try myself even though I can't, and support me with that. Another day is giving me more support when I need more support. And I want to have this kind of empathy in the robot as well. And I truly believe with passive PCIs, we can create that kind of empathy in these robots. And like I said before, I think we can, if we go to conversational AI, if I talk longer to an LLM, it will get so much faster and better to my model, to the model it has for my personality, if we do neuroadaptively. So, and I mean, we create now this development environment. We have the hardware, the software, the classifiers, the ideas, and you can use that. I mean, not only from us, other people do the same thing, but this is an open space. There are so many questions that need to be answered, so many possibilities to apply this kind of technology. This is a new type of technology. If you combine generative AI with neuroadaptivity, the outcome of that is a new type of technology. And I really invite you to join us and do this work and see what we can do with that. Thanks for your attention.
Can I ask a question?
Yeah, please, of course.
First of all, thank you for your great talk. I have two questions. First is about some technical questions. So, it is possible to teach the neural network using other types of neural network, like for example, teacher-student setup or the knowledge distillation. So I was wondering, is this kind of like neuroadaptive AI is also performing much better than this kind of network teaching networks?
I wouldn't say that's either or. I mean, I think it would do both. I think there are some things you can learn from the teacher networks and some things you can learn from the human. It also depends on whether the human can be put into the same context. Both of the systems need to, so the human and the AI need to see the same context, right? And I think I truly believe that there is some information you can derive from the brain that you can't get out of these other networks. I mean, there are these models that try to provide reward for physical AI with an LLM or VLA, and dopamine is one example of that. That is doing exactly what you say, right? And we're currently exploring that. How good is dopamine alone? How good is our brain reward function in that scenario? And how good is it if we combine that? I think the combination in the end is the best one we can do.
And the second question is that I think your previous results were mostly focusing on the performance or like kind of accuracy of the network. But we can measure like different metric from a same neural network model. Like for example, we can measure how generalizable this network or how this network can behave in continual learning scenarios, something like that. So do you have any plans to like evaluate your network on the other context?
That's a very good question. This is exactly, I want to convince my team to get away from these classification accuracies and all that, because I think that is a good method for comparison. If I want to compare one algorithm that decodes mental state to another, that's a good algorithm. But in the end, we need to see how we can improve the performance of a system. And then it doesn't matter what the accuracy is. So if I put my brain data into an LLM, providing some annotations, I don't care whether the detection was 70 or 80%. I need to see how good the LLM is, how much better it is with all the brain input. And that's what we're currently doing. We are now working with Google DeepMind on that. And we want to find out how we can improve things in these domains.
Yeah, and follow up on the previous question, the idea of distillation, which is very similar to what you said. So you have like a very complex model, that's the brain, training a simpler model, the same thing. Now the issue, with human brain is the bandwidth. Like, you can only ask one question, so, and we might need 100,000 questions to get proper distillation. Could we imagine, I don't know, we have people on hospital beds and I don't know, they're sleeping or something, we keep their eyes open, we're streaming images, recording tons of data to increase the bandwidth so we can build, proper model distillation.
Yeah. I mean, so the thing is, yes, we can only ask so many questions, but the frequency of the output is really high. I mean, when I look through the room, basically everything I look at will be annotated by my mind. So we get really a high frequency output compared to the low frequency output we usually have when we ask questions or when we give a button press or something. And this can be used by what we call, there's a paper out there on this cognitive probing. So what you just, it's basically exactly what you just said. We can display something to you. You don't need to have people in the hospital, but you put your VR on, and then the system decides, I don't know whether Arno likes the color green, and then shows you color green and sees how you respond to that. And with that, it can update its model, and it can do that, encode that maybe in your natural interaction. So suddenly cursor is green, and then you respond to that, and you don't even realize, right? So there are multiple mechanisms that you can encode information into your daily interaction, probe the mind with that, and provide this, get the output of that. And yes, maybe the accuracy is not really high, then you do it 5 times, and then you know what the result is. And I'll show you the first time a green cursor and you liked it, then I don't know if you like color green, then we know you like color green. I mean, that's a simple example, right? But basically, the dimensionality of the output goes higher. You have like 10, 20 mental states you can detect at the same time. The frequency of the output is high. And when you compare that to other learning algorithms, it's really, really fast. You don't have to always formulate a complex question to get an answer from the brain.
Is it possible to quantify the attention, like in terms of to reduce the dimensionality of the output?
I mean, so attention is a mental state we can derive, and we can also see how you are capable of attending to things. I mean, how stressed your brain is at the moment, and you can identify, classify to do that. Yes. Was it your question? Or?
Yeah. So my question was that, like, if you apply this attention to reduce the dimension of the output, like, for example, even if you receive many kind of like seeing information in the visual system, you will attend only a specific part of the scene.
Yeah.
So if you can like measure or quantify this attention by real time, then you can reduce the dimension of the output.
Yes. I mean,
it can make scalable.
Yeah. Then you can adapt it. So there's a smart thing we can do with large language models or AIs, that you can adapt the context in a way that's matching you perfectly and asking the right question or giving you the right amount of information you need at the time. And that's the power thing. When I mentioned earlier, you have the generative AI on the one hand, and then the neuroadaptivity on the other hand. If you combine them, the system can adapt to you, and your mind can adapt to the system. And that is a super powerful approach.
I actually had a question on the sensing side. I think the patch that you showed is very promising that it can pick up EEG across electrodes. Have you considered adding more sensors, like looking at PPG at the same time, eye tracking, or do you feel like that's not going to add enough value versus the burden of somebody, having glasses show it?
Yeah, no, that's a very meaningful question as well. And so my approach would be, let's take the simplest sensor or measurement device that gives the best output. Unfortunately, I think I know 7 reasonably good studies that compared knowledge extraction from these other measures into the BCI, and the BCI always outperformed everything. And even adding like GSR, heart rate, whatever, to a meta classification didn't improve much. The problem is, I mean, the thing is, it makes sense. The brain is the center of all. Everything is flowing together in the brain, and any other response is secondary. And I mean, the timing of the EEG is super powerful. It's milliseconds, and the rest is rather slow. What is good is, I mean, to provide more context information. Therefore, it's good. So, for example, eye tracking tells me where I look at. And I mean, when I have a surprise in my brain, I don't know where this is coming from. I mean, if it's auditory, it might be to the auditory signal. But when I look at the mouse running here, that's the mouse, of course. I look at the mouse, they're surprised. The system knows, okay, the mouse was surprising to Thorsten. So that is meaningful, but to derive any cognitive information from that other than information perceived, no. It doesn't help much.
How much context do you think would be needed in this sense?
Yeah.
In your mouse example, it would be nice to have a camera looking at the whole
scene. Yeah.
To know that there is a mouse there, but then it's even more context to have eye tracking to know that you're looking at the mouse. But is it enough to just have a full view of the scene and see similar signals every time you've seen a mouse in like the past
month or so, and then that's enough to create that context that the mouse is what's creating the suppressed signal? Or do you think, you need more sensors than just that?
To be honest, I can't answer this question precisely, but that is when I say the power of the LLM comes into play. I mean, so firstly, of course, the more information we have actually about the context, the better it is. But what do we need in the end? Depends on the power of the AI, whether how much knowledge it has, how big the memory is, how much it can relate the patterns in your mind to the patterns in the context. I don't know. I mean, what we are seeing right now is that you have glasses or other sensors you wear around with you, which are constantly assessing the context. The more we have from that, the better we can interpret the BEG. But clearly said, we need that. We need information about context. How much? Let's see how this evolves over time.
I'm curious about how to make full use of real human feedback, because I think the human feedback is hard to get in practice.
I mean, the brain data is, of course, human feedback, right? And we see that we use, for example, like I mentioned earlier, button presses, like responses to LM output. And that is super powerful. That was one of the big differentiators in the development of ChatGPT. So my assumption is that if we use the brain input, it will be more powerful. How? Your question is how to do that, right? And
my question is how to reduce the data of the human feedback, for example.
How to reduce?
Yes, because when we improve the model,
Mm-hmm.
improve the output, we need to get a real feedback from the human to evaluate it is good or not. But during training, the human feedback is not always available during the training. So how to deal with this issue?
I mean, the thing is, we do this with implicit input, with passive BCI, where you don't need to put full attention to that or communicate that back. But if there's no human available, of course, then we might be able to create a artificial annotator, right? That a system, generalized model that has seen, like, say, 10,000 people responding to a certain task and could replicate that. But that is something we are actually currently working on to see how good that is, but that's a little bit further in the future. But I think we can create such a generalized cognition model when we have collected enough data. But there, the 4,000 people we have will not be enough.
Brendan's a question.
Oh yeah, Brendan. Hey, hi, Brendan.
Hi, Thorsten. Good to see you.
Good to see you.
As I'm sure you recall, we have discussed the definition and key features of a BCI many, many times over the years. I believe from your talk that you still seem to agree a BCI has 3 features, and the question is, I'm just checking with you. First, it has to record directly from the brain. Second, it must involve some real-time processing. And third, it has to present feedback to the user, even if it is not overt feedback, such as adjusting the difficulty. Is that correct?
Yeah, if you speak about BCIs, that is correct. So this is why I'm also transferring to the term neuroadaptivity, which allows for a broader spectrum of that. But in general, yes, I agree that BCIs have these 3 features, yes.
Thank you. I will email you with more questions.
Great talk, very cool
Thanks.
stuff. And in general, the passive BCI neuroadaptive field has been very impactful in the way I think about the brain in general. So I'm gonna ask you a question that's more focused on the classifying of these different states. It seems like from an experimenter's perspective, we invoke a lot of theory when we're deciding what is happening in a certain task, right? And that's probably what led you to train certain classifiers for surprisal, error processing, whatever. However, like our understanding of the cognitive processes behind some of these responses is changing. So, I studied the P300, and I know from being very deep in that literature that the BCI world is at least 20 years behind in what we actually believe the P3, especially the P3B, is reflecting. So, if you look at the card oddball style task, it's going to be scoring high on some classifiers that are based off of some theory, which are sort of directly embedding experimenter restrictions on the qualia that the the alignment is going to be biased by. Is that the end goal, or is there some more like direct brain to alignment pipeline that you guys are thinking about that sort of skips this predefined classifier stage?
Well, it's a bit, my answer is a little bit complicated, I think. I can't answer it. It's not, I don't see a way to answer it very simply and directly. But what I mean is, yes, we define the classifiers in a certain way. We have our calibration paradigms, which are basically built on a concept of the mental state. And then we have this P3, P3B, and whatever is encoded in that paradigm is then reflecting a mental state or generating a mental state, and we put some idea what that means into it. But what I would say now is it doesn't matter what we interpret into that. We create this classifier, and let's say we currently have 7 P300 classifiers.
Sure.
And I can't tell you the difference between those, even though the paradigms are very different. But when I provide this to an abstract AI, an LLM, and describe how the classifier was trained, it gets an understanding, not in one word that is surprise or whatever, it gets an understanding how it was trained. And then the LM has an idea what the classifier could mean. And then over time, it gets situative understanding and sees how the classifier responds to it, and then learns over time to describe what the classifier output actually means. And then maybe we can learn from that what it actually is. So I don't believe that a P3 is a surprise signal or whatever. I don't know that, but also I see that I likely will not be able to explain that fully. But maybe when we have an LM that learns over 2 years from your brain, it might understand what this classifier actually is reflecting in your mind.
Understood. So in that same vein, it's able to up and down weigh the individual classifiers, right? So I can just say, oh, this one is actually correlated to these other 2, and so we don't need it. We can just keep these other 2.
Yeah, that, but also could update its internal description of that classifier. Then depends, okay, I want to now see this. I don't have maybe, so what I truly believe is the response in our brain, or the signal in our brain, I don't know if we can describe that actually. I mean, I don't know if we have a word for that, right? It's a concept in our mind, and that describes something, and it might get close to surprise or error or whatever. But I mean, so the motor cortex is not only controlling my hands, it also is active when I think something. So this is why it's good that I take a walk when I think something through, because it's activating the motor cortex. So we don't know actually what is going on in the brain. And so I think the system over time might have a way better understanding what the signal means than what we initially put into.
Sure. Thank you very much.
Can I make a brief comment?
Yeah. Makoto.
Nice to see you again. And thank you very much for a nice talk. I have one comment about the EEG ERP side. And I can make one prediction here that if you change the interstimulus interval between your trials, then that can probably affect your, the learning or prediction results. And it may be the case that using the longer interstimulus interval, which is more boring for the subjects, but because they have to wait longer. But there is a very robust effect that a longer interstimulus interval increases the extra-lemniscal thalamic responses.
Yeah.
And if I understand it correctly, many of your the experimental designs and the paradigms takes advantage of this extra-lemniscal thalamic responses. And this extra-lemniscal thalamus is sensitive to the interstimulus interval. And up to 16 seconds, which is quite a long time, right? Up to 16 seconds, this onset evoked potential goes larger and larger, this amplitude.
Okay, that's interesting.
And I'm not sure that larger onset evoked potential means more accuracy, as if you magnify the brain response. I don't know that. But if there is ever an interaction between the levels of the surprise and the onset evoked potential, which may or may not. So this is an empirical question, right? You have to test if the larger onset evoked response means more like the accuracy or the resolution of the mental process. So this is a testable hypothesis. And I want to also make sure that these onset evoked responses are modality independent, which is kind of natural, right? Because your surprise must be independent of your input modality. So visual, auditory, sensory, olfactory, anything can trigger. So any sensory, any like sort of the sensory input can trigger your surprise. That's why this extra lemniscal thalamus is modality independent, and it is considered to code some kind of a saliency of the input stimulus. So, and I wrote one paper published last year about focusing on this topic, actually. And it was such a surprise for me too, because we typically discuss, oh, this is the auditory evoked response or visual evoked response, or sensory evoked response, which is this ERP peaks and the troughs around 100 and 200 millisecond-ish. These are not sensory specific, actually. These are almost all like modality independent ones. So, and a very simple proof for that is that if you make the longer interstimulus interval, regardless of auditory, sensory, visual, they show larger the amplitude in the ERPs. So this is a direct evidence that these are not necessarily auditory or any domain specific responses. That was my comment.
No, thanks, Makoto. That's really very in line with our goals and very helpful. So we want to create the classifiers in a way that we get the strongest and clearest response we can get. So the classifier can identify that signal very clearly. It will not maybe be as clear in the real world when you go into a realistic task, but we want to have the prototype of that. And therefore, your suggestion is really helpful to extend the interstimulus interval to get a stronger response in the end. Whether it reflects more attention or not, let's put that aside. And secondly, we want to go, I mentioned earlier, we want to have these dimensions, the primitive dimensions of the mental state. And therefore, we are currently collecting different examples of P300s evoked from different sensory input or different modalities, and try to find the core principle of that, which is exactly what you're referring to. So that's really very helpful, and that's exactly where I want to be at. And I will read your paper happily and see what we can learn from that.
Thank you. Yeah.
Actually, I guess this is a little more based on going off of what that it's just trying to understand. Like, it's very fascinating that you were able to show this kind of like being able to associate the waves, the recordings, and training models based on them. But as you're saying that it could be like eventually extrapolated to being able to do a much more complicated analysis of being able to train much more complex sets of data just by the response that the brain is giving. But do you feel like to be able to do that, it would be better to have to characterize what signals the brain is giving out, or?
Yeah, I mean, we definitely need a characterization of the signal we're getting out there. We need to have a starting point, right? We need to. I hope I get to the right direction to answer your question. But I mean, we need to have an idea in what direction that signal might go. If we go for P300, our best description now is maybe surprise or some other papers we read about that. And then we say this could mean surprise on this and this. So we have, let's say, my current approach is we record a signal, we have a description of the paradigm, and we have a description of the theory. And then we have these sections and put that into the LLM and say, this is what describes the signal. That's a starting point, but the system is able to adapt that. It can learn, it can adapt that text by itself. So the description of that paradigm is at a starting point, which is hopefully close to what it really is. And then over time, it will learn to improve that description. But that's a theory, right? I don't know whether that really works, whether LLM are really capable of doing that. But I mean, also, we don't know where the LLM world or where the AI world will be in a year or something. I mean, things are going so quickly. So that is a bet also on the capabilities of the systems. But that is my current approach to that. Thank you.
Yes, sorry. I didn't so I'm delighted to hear some of the discussion about the P300 and the very correct observation that much of the BCI community lags behind in key knowledge. And I think you, Thorsten, agree on that. One major comment that I want to help get out there is I still see papers all the time that use the so-called oddball paradigm under the presumption that the standard stimulus is necessary. This is not accurate at all. C. Gonzalez and Polich, 2002. This is a great paper. I was a postdoc under John Polich out in San Diego 20 years ago. And what he showed is, as the paper states in the title, ISI is the key determinant of P300 amplitude. The oddball component can be removed. The oddball component was strongly popularized in the 1970s by Donchin, Hilliard, Squires, and others within a mile of where you are right now. And I certainly mean no disrespect to that, or to those authors. But later work has shown that it's not necessary. Furthermore, as far as discussion of what it does, it can index surprise. It can also index attention, salience, fatigue, time of day, substances that are being used, perceived deception, perceived error, all kinds of things. So anybody out there who is interested in work with P3 BCIs, please feel free to email me. I'd love to discuss it. And I will also email Gerd about perhaps giving a talk for your group about this topic some week.
Yeah,
great.
Yeah. No, it would be great. And so that was Brandon Allison. If you can, okay. Thanks. Good to see you, Brandon. And take care.
You too. Thank you.
Oh, nice. Yeah, well,